I'm recording this in an effort to kind of clarify and slow down related rates for those who need to see it again. So we're going to redo the notes from yesterday in class. Air is blown into a spherical balloon at a rate of 3 cubic centimeters per second. That rate, and the key thing with a rate means that this has to be a something divided by something. So cubic centimeters is centimeters cubed, per second is over seconds. This is a change in volume over a change in time. But we don't use the delta notation when we're talking about an instant. We use the d notation, dv dt. So dv over dt is in units of centimeters cubed per second, and that's a change in volume over a change in time. And the question's asking how fast is the radius of the balloon increasing. So when it says how fast and increasing, that also refers to a rate. So if I define radius as r, then I'm going to want to call this dr over dt, change in radius over change in time, and that's going to be in units of centimeters per second. That nose blow was Richie. So we want to know what's happening at the instant when the radius is 4 centimeters. So I'm going to say r is equal to 4, but I want to be clear that this is an instant. Now if you go down into these two graphs, these graphs are going to kind of create sort of visual of this, at least in terms of this. This right here represents dv dt, at least the slope does. The change in volume over the change in time is constant, and it's a constant rate. This equation of the first graph is a constant rate of 3 cubic centimeters. So if I kind of plot this as volume versus time, as the graph indicates, then this is volume with respect to time is equal to 3 times t. And that should make sense if I take the derivative of both sides. dv dt is equal to 3. But we know that's what it's 3 cubic centimeters per second. So again, this represents just the slope of the volume versus time graph. Now, we're trying to find dh dt, and yes, sorry, not dh dt, dr dt, and yes, they are related. They're related because as radius increases, volume increases, but they might not be related directly, and that's the problem. This graph here represents radius versus time, and you can see as you blow up a balloon, you start here, then you go here, then here, then here. It's a spherical balloon. The larger you get, the slower the radius grows. It first has an initial growth that's really large, but then it kind of slows down. This blue line here represents a tangent line, and that's the if I take the slopes at individual points, you can see the slopes are starting to flatten out. They'll never get perfectly flat, but the radius growth will slow down. So to do this, we first are to figure out what dr dt is. First of all, dr dt is changing, so I want to find what dr dt is right here at time. Let's see, when r is equal to 4. I want to find it not when r is equal to 4, or when r equals 4. This is radius versus time. But at the moment when radius is 4, so right here, just kind of some unknown point over there, I want to figure out what that slope is. So let's kind of come back to the formula for the volume of the sphere. That's how we are going to relate this. Volume is equal to, you guys should know this, 4/3 pi r cubed. Now, the key thing with this is we're going to do implicit differentiation because there is no time t variable present, but I'm going to take the derivative of both of my two variables, v and r, with respect to t. So what that means is that the derivative of r with respect to t is dr dt, and the derivative of v is dv dt. So I'm going to take the derivative of both sides. Derivative of the left is dv over dt. And then we're going to do the derivative of r. So I'm going to do chain rule. Let's do the outside first. This is going to be 3 times 4 pi r squared. But then by chain rule, I have to do the derivative of r, which is dr over dt, if I take it with respect to t. Usually we've taken the derivative with respect to the input variable. That would be dr. So if I did this and derived it with dr, I would get dv over dr is equal to 4 pi r squared. That's change in volume with respect to change in radius. I'll leave it up to you to realize that that's also surface area, but that's not the equation we're looking for. I'm taking it with respect to t. Now, to find dr dt, I know that dv dt, way up in the original problem, was equal to 3. I know that I was doing this at the instant that r was equal to 4. So if I substitute 3 in for dv dt, 4 pi, substitute 4 in for r, we get 4 squared is equal to dr dt, or times dr dt, and I solve for dr dt. I'm going to get dr dt is equal to, this is going to be 3 over 64 pi. And my units of that are going to be, sorry, I forgot what they are, centimeters per second. So that's the change in radius over the change in time, but this is only at r equals 4. So the process we're going to use is going to be a little bit more simple. The key equation that we needed is the one that related dv dt, dr dt, and technically dv dr, but these are the two we were looking for. So the equation that relates all these can be found by taking the volume equation and differentiating, which means taking the derivative of each variable with respect to time. In our problem, we have volume is equal to this, and we took the derivative of all variables with respect to time. Now, some examples of this: suppose that we have an area of a square with side length x. So I'm going to draw a square with x as a side length, all sides congruent, and the area is increasing at a certain rate. Since I know it's asking for the area, let's just say the area of the square is equal to x squared. And if I differentiate this function with respect to time, I get dA over dt is equal to 2x times dx over dt. And that's a second equation that relates the change in area to the change in side length. If I have a rectangular solid with a square base, and that's increasing at a certain rate, so my rectangular solid with a square base would just look like this: square base, and some rectangular solid just kind of up here. Usually not great at drawing these, but I will try. Okay. So there's a rectangular solid, square base x, but it's an unknown height, so we have a different variable. So my volume would be equal to x squared h, and if I differentiate each variable with respect to time, I'd have to use product rule. dv dt equals first derivative of the second, so the derivative of h is dh dt, plus second derivative of the first, so 2xh, and the derivative of 2x would also include dx dt. So this would be an equation with product rule that would relate the change in volume to two variables. Now, oftentimes we're going to be taking one of these variables, like h, and solving it with respect to the other one, and we'll show you that here in a minute. So here's the basic steps. You may want to picture a diagram and label it so you know what you're looking for. You also want to identify any constants, and we'll show you that here in a minute. You write down everything you know about this, so all the equations that you're aware of, or that you know what to do. You write any equation that relates the variables, and then you take the derivative of everything with respect to time, and then you substitute in what you know and you solve for what you don't know. Let's go with the spherical balloon. This balloon's inflated with helium at this rate. So right now I know that since it's inflated at that rate, that is dV over dt. How fast is the surface area increasing? So we've already used volume and surface area. I need a volume equation, 4/3 pi r cubed, and I need a surface area equation, 4 pi r squared. You guys have all had geometry. You're not going to be given formulas for volume and surface area of spheres and other solids. You need to know those. We're going to be using them a lot, so it's just a matter of, like, when it comes up, make sure you review it and make sure you know you can either look them up or then, you know, once you've looked them up, memorize them so you can use them later. I'm not going to give them to you on a test. Alright, so these are the two. It says, how fast is the surface area of the balloon increasing at the moment when the radius is 5? So I know r is equal to 5, and I'm looking for dSA dt, this derivative of surface area with respect to time. So I'm going to want to take this and differentiate it. dSA over dt is equal to 8 pi r dr dt. I know r at the moment where I'm looking for. R is 5, but I don't know dr dt. However, I can use the volume equation dv dt is equal to 4 pi r squared dr dt to solve for dr dt. Since I've given that dv dt is 100 pi equals 4 pi, r would be 5, so that's 25. dr dt is what I'm solving for. If you solve this, you get that dr dt is equal to 1. So let's plug that in here. And I would get dsa dt equals 8 pi, radius is 5, and dr dt is 1. And that would give me 40 pi, we always want to put units down, feet squared per minute since it's a surface area. Next problem, two jets are flying at 520 miles per hour along straight line courses that cross at right angles. How fast is the distance between them closing? So if I have a jet flying this way and a jet flying this way, they're flying at straight line courses that cross at right angles. So this means that kind of how we're doing, and the distance between them is represented by a straight line distance. That's a diagonal of a triangle. So this is kind of the picture. I can fly, I can show one airplane and show the other, but what I'm going to do is define these distances. So this distance, let's just call C. You have airplane A and airplane B, and we just created a triangle. Now, at the moment when airplane A is 5 miles from the intersection and airplane B is 12 miles from the intersection, I think you can all establish what the distance between the two planes is by just a basic 5, 12, 13 Pythagorean triple. So if I know that, this is a moment, this is like a snapshot, but I'm looking back at the original one to decide how this is all changing, because as the planes get closer, the distance is changing. So I can't just say that they're always 5, always 12, and always 13 apart. What I'm going to do is, I'm now going to say, relate these. So a squared plus b squared equals c squared. And if I take the derivative of everything with respect to time, I get 2a times dA dt plus 2b times dB dt equals 2c times dC dt. Oops. dC dt. And we can cut the 2's out. So we need dA dt and dB dt because the question's asking how fast the distance, it's asking for dC dt. Well, dA dt in this problem, it says that the planes are traveling 520 miles per hour, but the distance is closing. So my change in area, or change in A value, A is the distance here, over change in time, should actually be a negative 520 miles per hour because the distance is getting smaller. And my change in B is also a negative 520 miles per hour. And C should be also, dC dt should end up being a negative value, representing that the distance is getting smaller. So now we can substitute. A would be 5 times negative 520, plus B is 12 times negative 520, and that equals C is 13 times dC dt, which is what I'm solving for. Well, 5 plus 12 is 17. dC dt would equal 17 negative times 520 over 13. 13 goes into 520 40 times, and 40 times negative 17 is negative 680. So they're closing at negative 680 miles per hour. Let's see. From let's go to number 5. A 13-foot ladder is leaning against a house when its base starts to slide away. So here's a house, and here's a ladder, and this is 13, and its base starts to slide away. So let's call this base, and let's call this height. By the time his base is 12 feet from the house, so at B is equal to 12, the base is moving at a rate of 5 feet per second. So dB dt is equal to 5 and it wants to know how fast the top of the ladder is sliding down the wall. It wants to know what dH dt is. So let's just do an equation that relates all of them. Again, that's a Pythagorean theorem, so h squared plus b squared equals, and 13 squared is a constant. That 13 is never changing, even though h and b are. So when I take the derivative, 2h dH dt plus 2b dB dt, let me zoom in and make this a little clearer, is equal to, the derivative of 13 squared is just 0. So if I solve for my dH dt, dH dt is going to be equal to negative b times dB dt all over h. And if I substitute, well, I need to figure out what b and h are. It says at b equals 12. Well, again, we just have the same triple. When b is equal to 12, h is equal to 5. So I can say negative 12 times dB dt is 5 and h is 5. That means that dH dt is negative 12 feet per second. And that makes sense because the height is decreasing. Then it asks how fast is the area of the triangle formed by the ladder, wall, and ground changing. So the area is equal to 1/2 base times height, and d area dt is equal to 1/2, we're going to have to do product rule here. First derivative of the second plus second derivative of the first. So what we get is 1/2, b is, let's go back up, b is 12, and dH dt is negative 12, plus h is 5, and dB dt is 5. Check the signs on that. Then we get 1/2, negative 144 plus 25, or negative 119 over 2, and that would be in units of feet squared per second. Okay. Next, two trucks leave a depot. One of them travels east and one travels north. So we can call this distance A and this distance B. We have a distance between them. So I know that dA dt is equal to 40, dB dt is equal to 30, and we don't know what dC dt is. It says how fast is the distance between the convoy changing 6 minutes later. 6 minutes is 1/10 hour. So 1/10 of an hour later, A would have gone 40 times 1/10, or 4. So I know that A is equal to 4. I can draw a second triangle with this. A is 4, and B is 1/10 times 30. B would be 3, and that means that C would be 5. So let's just write the a squared plus b squared equals c squared equation. When I take the derivative, I'm just going to cut the 2's out right away. So a times dA dt plus b times dB dt equals c times dC dt. And I get a is 4 times 40 plus b is 3 times 30 equals c, which is 5. Let's just divide by c, so I can have that equal to dC dt, which would mean this is 4 times 8 plus 3 times 6, or 32 plus 18, and dC dt would have to be equal to 50 miles per hour. Okay. Finally, you have a balloon rising vertically above a level street at a constant rate of 1 foot per second. So just when the balloon is 65 feet above the ground, a bicycle passes under it going 17 feet per second. So at the moment that the balloon is 65 feet above the ground, a bicycle is under it, so we can just kind of draw this 65, and here's a little bicycle. That's my bicycle. How fast is the distance changing 3 seconds later? So 3 seconds later, going at 1 feet per second, this bicycle has gone 51 feet. So this is 51. I know that 3 seconds later my balloon has gone 3 feet, so that's 68. And let's see, how fast is the distance between the bicycle and balloon? So this is an unknown c. Well, I can say c is equal to the square root of 68 squared plus 51 squared. While I kind of pull out a calculator and start doing that, we can go ahead and set up our equation. I know that this is just going to be a basic h, base is b, and we can call that c. So I know that it's going to be h squared plus b squared is equal to c squared. Again, we're going to get rid of the 2's, so when I take the derivative, it's just going to be h dh dt plus b db dt equals c dc dt. So let's see, 68 squared plus 51 squared, square rooted, this is 85. And if I just substitute values in and solve for dc dt, I get dc dt equals 68 times dh dt was that 1 feet per second. Oops. This is dh dt. The bicycle traveling was db dt, and the b was 51, so that's 17 over c, which is 85, and 68 plus 51 times 17 divided by 85 gives me dc dt is equal to 11 feet per second.